Okay, I hope I am audible and my screen is also visible. So let's start our ninth tutorial session. Okay, so this is tutorial 9. Tutorial 9, Advanced Linear Algebra. This is NOC 25MA03 and today is 22nd March of 25. So today in today's this tutorial, I will do some assignment problems, some problems which will help to solve the assignment, as well as I'll try to do some problems which are which are appeared in the previous year, some previous year NET exams uh, or linear algebra. So let's start. We'll first do some problems which will help to solve the assignments. Okay. So for this. Um, For this, what I will first, okay, what are my plan? Just I need to let's check my plan. Right. That, okay, just a minute. So let's first do. We have seen in last tutorial we have seen the Jordan canonical form, how to find a Jordan canonical form. So let's repeat once, and after that go to the we'll we'll go to some other problems. So Jordan canonical form, there's let T, that is one theorem. That the theorem is let T from V to V be a linear operator on a finite dimensional vector space V over a field A. Okay, and uh, let um, let mx or px is equals to x minus c1 whole to the power r1 all the way x minus ck whole to the power rk, and fx is equals to x minus c1 whole to the power d1 all the way x minus ck whole to the power dk, where c1 c2 all the way ck are all distinct eigenvalues or characteristic values of V. Let this is the minimal polynomial. This is minimal polynomial, and this is characteristics polynomial. Characteristics polynomial. So therefore, algebraic multiplicity of Ci, that is equals to obviously Di, and geometric multiplicity, this is equals to the dimension of the eigenspace dimension. So this will be a geometric multiplicity of Ci, dimension of the eigenspace of Ci, that is equals to all dimension of the space, that is equals to dimension of the space all those x belongs to vector V such that T minus Ci identity x is equals to 0, dimension of this space. Okay, so we know if algebraic multiplicity of Ci is equals to geometric multiplicity of Ci, that implies that if and only that T is diagonalizable. Okay, now I just want to say here is that let corresponding to Ci, consider a block corresponding to Ci, consider a Ri cross Ri order block like this way: C1 1 0 all the way 0 0 Ci, this is Ci 1 0 all the way 0, and in this way the second last entry will be 0 0 Ci 1 and the last entry will be 0 0 Ci. So this is a matrix, this is an Ri by Ri order matrix where the main diagonal entries all are Ci and the upper sub diagonal entries, sorry, um, diagonal, I mean entries above the main diagonal entries, those are actually 1. Okay, so in that case let's consider Ri order block, and these are the block, and let's like this is as Ai. Okay, then the Jordan canonical form of T will contain blocks like Ai corresponding to the eigenvalue Ci in the following way. First is that the following way. What is the following way? Says that at least it will contain a block. It will contain at least one block. Contain at least one block of order Ri cross Ri. Note that this Ri is actually the multiplicity of Ci in the minimal polynomial. Okay, so in the all other block corresponding to all other block corresponding to Ci will be of the form A with order. Okay, that I'll write something AI. This is AI of the form AI with order less than is equals to Ri. Okay, this is the first thing. So that means at least one block will be there which is of order. At least one block will be there which is of order um, uh, what is called Ri cross Ri, and all other block corresponding to Ci will be less than equal, order of will be less than equals to, and the third one is, and the maximum number of, and the total number of blocks, not maximum, total number of blocks corresponding to um, total number of blocks corresponding to Ci is equal to geometric multiplicity of Ci. So let T be a nilpotent linear operator of index for if the nullity of T is 3, then the block diagonal matrix representation of MT of T is what will be the blocks. So the nilpotent operator of index 2, index 4, that means that means therefore let T from R7 to R7 be a nilpotent nilpotent operator of index 4. Okay, nilpotent operator of index 4, nilpotent operator of index 4. Therefore the minimal polynomial is x to the power 4. Okay, and there on clearly only eigenvalue of, as note that note that only eigenvalue of a nilpotent matrix is 0. So therefore, the minimal polynomial, therefore only eigenvalue is 0. Okay. So therefore, the Jordan canonical form of T must contains a block of the form 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0, a 4 by 4 block. Okay, because this is the multiplicity of the eigenvalue 0 in the minimal polynomial, so there should at least this number of polynomial should contain. In the second factor, what it is given that if the nullity of t is 3, now also it is given that also it is given that nullity of t is equals to 3. Nullity of t is equals to 3. Therefore, that means the dimension of the eigenspace of 0 space of 0 is equals to 3, that is equals to the geometric multiplicity of eigenvalue 0. So therefore, as the geometric multiplicity of the eigenvalue 0 is 3, so therefore the Jordan canonical form Jordan canonical form must contains exactly 3 block. Okay, so what are the options? Let's see. Okay, we can directly say that as one block should contains this type of one this type of block should be there. So therefore, option 3 is the only correct option. All other options automatically becoming fails. But what are the two blocks is possible? Other two blocks is only possible. So therefore, other two possible blocks must be of the form 0 1 0 0 0, because we have taken already 4. We have taken already 4, so we have 3 left. Okay, we have to make an 7 by 7 order matrix, and we already take 4 by 4 order matrix block matrix here, so we have to make 3 by 3 order matrix. So therefore here we can only take 2 1. Okay, we can't take 3, because we have to, if we take 3, then there will not be left anything to make any other block. So we have to take only 2 1, and we can't take 1 1 as well. Okay, because 1 1, then we'll have 3 block, but the matrix will be of 6 by 6. So therefore the Jordan canonical form of T is equals to diagonal of with block 0 0 sorry 0 1 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0. This is one block, other block is 0 1 0, other block is 0. This is the diagonal form. Okay, so this is the thing. Okay, so let's do some other problem. Okay, but before this I'll just introduce the notion of the inner product. Okay, I'll just give a little definition so it will not be a problem. Let inner product space, let V be a vector space over a field A. So that means here we are not taking P is finite dimensional vector space or infinite dimensional vector space. So we are not taking anything. P is a vector space over the field A. Now an inner product on V is a function which assigns each pair, not ordered pair. Okay, let's write ordered pair. Ordered pair is equal because there is a conjugation. Ordered pair of vectors alpha and beta in V to a scalar. This is the symbol I will use for the inner product in the field A in such a way it satisfies the following property. Satisfies the following properties. What is the first property? Alpha plus beta inner product with gamma is equals to alpha inner product with gamma plus beta inner product with gamma. The second is that alpha C alpha beta is equals to C alpha inner product beta. This should be true for all alpha beta gamma from the vector space V. This should be true for all C belong coming from the field F and alpha beta coming from the vector space V. And the third one is that this is the conjugacy. This alpha is equals to alpha beta bar. Okay. This is the complex conjugations where bar is complex conjugate of inner product alpha beta. Okay, and the third one is that alpha inner product alpha greater than 0 if alpha is not equals to 0. So these four condition, if a, I mean, let's take V is a vector space over a field F, and for each ordered pair of vectors alpha beta, we are assigning a new element in the field F, writing as alpha beta, such that it satisfies the following condition, that is, this is called the linearity in first variable, and this is called the homogeneity, this may be homogeneity, and this is called the non-negative definiteness, and this one, if we use this first and third, then what we will get, we will get alpha comma beta plus gamma or C beta with this ABC, then we will get at alpha C bar, alpha beta plus alpha gamma. Okay, so this is something conjugacy, conjugacy of linearity happening in the second term. Okay, right hand side, this term. Okay, so this is called inner product. Okay, so now example of inner product is that one can define okay, here one can point out that if one takes V as a vector space over the field of real number, so in that situation alpha beta is an element of the real number. So in that situation alpha beta bar of alpha beta is again its bar of alpha beta is again inner product alpha beta. So there is bar does not doing anything. So now example is that let's take Cn is a vector space, that is the vector space, that is the vector space Cn over the field C. Okay, and here is the vector space, and let's take field is the where the this inner product is considering. Then inner product is defining from V cross V to the field F, that is C, by alpha beta for any alpha beta, that is by inner product alpha beta is equals to summation of alpha I beta I bar, where alpha is equals to, this is an n tuple alpha n in Cn, and beta is also similarly, beta is equals to beta 1 all the way beta n, that is again an element in Cn. Okay, so this is the example of inner products. So let's do one problem this regarding this inner product. Let V be the R square over R, that is the two-dimensional vector space over R. A vector space equipped with the inner product alpha beta is equals to given by this, whenever alpha is this, beta is this. Okay. So what is the inner product is given if alpha is equals to x1, x2, beta is equals to y1, y2, and it is given that alpha beta is equals to x1, y1 minus 2x2, y1, 2x1, y2 plus 5x2, y2. Okay, so alpha beta inner product of alpha beta is given by this way. Now one may ask that whether it is inner product or not. Okay, so in that situation we have to check all the four conditions, that linearity in first variable, homogeneity, and third is the conjugacy, and fourth is the non-negative definiteness. We have to check all this A, B, C four condition. If it is if it satisfies all the four conditions, then we say that this gives an inner product on the R2. Okay, but if it fails to satisfy at least one of them, then it will not be an inner product. Okay, but here it is said that the inner product is given by this way, so therefore this is an inner product. We are not checking that whether this is an inner product or not. But let's go back to the questions. What it is saying is that then yx is orthogonal to xy. Okay, so then we need the idea of orthogonality. Just a minute. Okay, so let's give the definition of orthogonality. Let V be a vector space over a field F, not field F. Let's V be a inner product space. That means that is a vector space. Okay, a vector space with an inner product is called inner product space. Inner product is called inner product space, or in short IPS. Okay, so let V be a inner product space over a field F, then alpha beta belongs to V are said to be orthogonal to each other, are said to be orthogonal to each other if inner product of alpha beta is equals to 0. Okay, so two vectors are said to be alpha orthogonal to each other if inner product of alpha beta is equals to 0. So therefore, if alpha is orthogonal to beta, then inner product of alpha beta equals to 0, and that will directly give that inner product of beta alpha is equals to 0. Therefore, beta is also orthogonal to alpha. Now, and we denote it by alpha. This is called orthogonal sign beta. Okay. Example of orthogonality. Let's take R is the vector space with inner product x and y is equals to summation of xi yi, where I equals to 1 to 2, where x is equals to x1 x2 and y is equals to y1 y2 coming from real number. So now note that here x and y are tuple of real numbers, so therefore we have not written the bar. Otherwise we have to take bar to satisfy all the four conditions. Okay, so here 1 comma 0 and 0 comma 1, these two are element in the vector space are orthogonal. Okay, so here is the question is that alpha beta is given by this way. So question is that then these two will be orthogonal when one of these condition will satisfy. Okay, now if 2y minus x is orthogonal to xy, 2y minus x is orthogonal to xy, then inner product of 2y minus x comma y, that should be 0. Okay, so but that implies that, okay, actually let's just check the answer. Let me check the just a minute. So this will give that 2xy minus xy. Okay, sorry. Okay, we have to use this formula. So therefore, here note that x1 is equals to 2y, y1 is equals to, okay, x1 x2 y1 y2. Then inner product is gained by this. Okay, so x1 is equals to this and x2 is equals to minus x, y1 is equals to x, y2 is equals to y. So let's replace all these things. What we get? That implies that x1 is equals to 2y, y1 is x, minus x2 is minus x, y1 is x, minus 2x1 is 2y, so therefore it will become 4y, and y2 is y, this is square, plus 5x2 is minus x, so therefore it will be minus, and y2 is y. Oh, x2 is minus x and y, so therefore it will be xy. This is equals to 0. So what we will get here, 2x square minus 4y square minus 3xy is equal to 0. So here it is written x in terms of y. So let's consider this is as a quadratic form equation. So x will be minus. So let's consider it is as a quadratic equation like this way: x square minus uh, plus minus 3 by 2x whole into y minus 3 by whole y, it is x, minus 2y square, that is the c term, equals to 0. So what we'll get? 3 by 2y plus minus root under 9 by 4y square minus 4ac, 8y square by 2. So therefore it will be 3 by 2y plus minus root under 32 41 by 4. I don't know where it is going. It's correct. I'm correct. 41 by 4 y square by 2. So therefore one can take 1 by 2y common. So what it remain? 3y plus minus root under 41. Okay. So and by 2. So therefore this will be cancel out. So what we have, we will have that y is into 3y plus minus root under 4. This is the answer. So what we have, 1 by 4, 1 by 4 is, sorry, this will, 1 by 2 will come and this will be 4. So this is the answer. 1 by 4 y, so 3 y is not there because I am taking y common. So this is not there. So 3 plus minus root under 4, this is the correct option. Other option is 1 by 2 is not the correct option. 1 by 2 is not the correct option. Here minus 3, so that's why it is not correct option. So this way we will be able to solve this problem. Okay. So now let's do some other problem. Let's add some instruction. Just to okay, so let's go to the questions number, another questions. Okay, let's do this. So here what is the question? Let v equals to r to the power 4 and t is the linear operator given by this. Okay. So t is the linear operator given by x1, x2, x3, x4 is equals to x1 plus x2 plus x3, comma x2 plus x3 plus x4, comma x3 plus x4 plus x1, comma another energy x4 plus x1 plus x2. So then the matrix representation of T with respect to matrix representation of T with respect to the respect to the standard ordered basis is given by, one can easily look at, one can take the order basis as 1 0 0 0 1 0 0 like this way, 0 comma 0 comma 1 comma 0 0 comma 0 comma 0 comma 1 like this way. One can take, this is the standard order basis, and one will get that the matrix representation of this linear operator T with respect to this order basis is given by 1 1 1 0 0 1 1 1 0, sorry, not, this is not 0, this will be x1 is there, 0 1 1, other is that 1 1 0 1. I hope this is correct. So this is the matrix. So what is the question it is asked? Let v be the v be r4 and t be a linear operator, and then the subspace z alpha t. Z alpha t is something, this is called in general the t cyclic subspace generated by alpha. T cyclic subspace generated by alpha. Okay, this is in general called T cyclic subspace generated by alpha. Okay, so if here are the polynomials. Okay, then dimension of Z alpha t it is asked. Now note that Z Z alpha t, this is equals to ft alpha, where f is the polynomial, okay, for some alpha vector is called T cyclic subspace generated by alpha. Okay. Now, as we know that here T is a linear operator, this is the matrix representation of T with respect to the standard order basis. That is a 4 by 4 matrix. So the characteristics polynomial will have maximum degree 4. So therefore, identity T, T square and T cube, all this will be the basis of the any polynomial in all will be the basis. I mean, any polynomial containing uh, 5, I mean, identity T, T square, T cube, and T4, that must be can be taken down to the, I mean, any polynomial. My point is that any polynomial ft can be written as a linear combination of like this way: c2 t plus c3 t square plus c4 t cube, like this way. Why it will be possible to write this way? Because if we have some with t4 t to the power 4, then we know that the characteristics polynomial will be some polynomial in considering 4 power, and that is equals to 0. Then we can write t4 in terms of t1 t2 t3. So therefore we can replace t4 here and we will get the terms in terms of t1 t2 t1 t square t cube and identity. So but the main point, but we didn't need to go all these way. So these are the things. So therefore the question is the here it is asked that the what is the dimension. So therefore the dimension of this space can be maximum 4, because that is the alpha, t alpha, t square alpha, t cube alpha. That will be the maximum dimension. Okay. So that will be the maximum, I mean, that will be the maximum linearly independent set. Okay. But we can show that here the matrix T, uh, T with the vector, here alpha is given here, generated by alpha is equals to, this is given, alpha is the vector, given that minus 1, 1, minus 1, 1. That is minus 1, 1, minus 1, 1. So one, if it writes, if one writes like this way, minus 1, 1, minus 1, 1, that will be 1, 1, 1, 0, 0, 1, 1, 1, and 1, 0, 1, 1, 1, 1, 0, 1. I think this is the, yeah, yeah. So this, if we multiply with minus 1, 1, uh, minus 1, 1, so that what we'll get? We'll get that minus 1, minus 1, plus 1, 0, and minus 1, plus 1, minus 1, minus 1, plus 1, minus 1. Next is minus, next is the except third sum of all. So therefore that will be 1. Next is the except fourth sum of all, that will be minus 1. And next is the except first sum of all 3. So that will be 1. So therefore we will have this one. So note that this is the alpha, this is alpha. Okay, this is alpha. So therefore what we are getting that the T alpha is equals to alpha again. Therefore, for any polynomial phi t, for any, therefore, for any real polynomial f in this Rx, f t alpha, that is again it will be f of 1 dot alpha, right? That is clear. That will be clear. So therefore, every element of this Z alpha, this T cyclic subspace generated by alpha, Z alpha T, is scalar multiple of alpha. Therefore, the dimension, of Z alpha T, that is equals to 1. Okay. So this gives the answer. All other options are then incorrect, because this is exactly accurate questions. So we don't need to go any other. So let's go to the other problem. Okay. before this, I just want to do something. That is, suppose now suppose we have a linear operator. Okay, no, questions is something different. One can assume. I mean, okay, constructing. We can write it as a constructing inner product by the help of a linear operator. By the help of a non-singular linear operator. Linear operator. What it says, let V and W are two vector space, need not be finite dimensional, two vector space over a field F, J, and T from V to W be a non-singular linear operator. Recall that T is non-singular, that is if and only T alpha equals to 0 implies that alpha equals to 0. Okay, so that means that this is injective. Main point is that T is injective. Why I am taking T is injective, that I will say. And let an inner product from W cross W to the field F is given, then one can construct a new inner product on V. Okay, how? So this is the construction process. Define, I am writing this from V cross V to A by taking alpha beta two vector is equals to T alpha. This is what I will write. This is as V and this is as W. Okay, alpha beta V, that is equals to T alpha T beta W. Okay, and why I now to check it is inner product, we need it is indeed a inner product. It is inner product. We proceed as follows. How will do? First case is the linearity in first variable. Let's take alpha 1 plus alpha 2, two element with beta v, that will be equals to T alpha 1 plus alpha 2 with T beta, that is on W. But we know T is linear, so we can able to write T alpha 1 plus alpha 2 as T alpha 1 plus T alpha 2 comma T beta, that with inner product W. But we know this is already a given inner product, so therefore this breaking is possible because this symbol is already an inner product. So therefore this is equals to alpha 1 comma beta plus alpha 2 comma beta. Similarly one can check that C of alpha comma beta v is equals to C alpha comma beta v for all C belongs to the scalar field F and alpha beta coming from the vector space V, and alpha beta is equals to beta alpha bar complex conjugate. But note that alpha comma alpha, that is equals to inner product V T alpha comma T alpha. Okay, W. That is equals to norm of T alpha square. Okay, this is the definition of norm. I mean, if I have a two vector, if I have a vector alpha, then norm is norm square is given by alpha alpha. This one, and we know this alpha alpha is positive, so norm is actually given by square root of this, because we know this is positive, so therefore we can define norm. Okay, okay. But the main point here I just want to make is that if t was singular, we can get singular, then there exists some vector alpha belongs to V which is not equals to 0, but P alpha equals to 0, and that would gives that P alpha square is equals to 0, and that would give inner product this alpha comma alpha V is equals to 0. that would that would contradict the that would oppose to oppose what that would uh, disqualify to become an inner product. So therefore that's why we are taking the T is singular. Okay, now on the basis of this we will just will what it says that consider the Euclidean space V equals to R3, that is V is the vector space of dimension 3 and equipped with the standard inner product on it, and the vector space P2R consisting of polynomial of degree at most 2. So given a linear operator T from this P2R, that is the space of all polynomial of at degree at most 2, to V by this way that T of a naught plus a1x plus a2x is equals to a naught comma a1 comma a2. So then the norm induced by T is given by what is the norm here it is asked. So we know that V is the R3. So norm on so basically I just want to write is that inner product on V, inner product V equals to R3 is a inner product space with standard inner product x and y is equals to, I can write directly instead of writing summation, x1 y1 plus x2 y2 plus x3 y3, where x is equals to x1 x2 x3 and y is equals to y1 y2 y3, and these are the element in R3, that is the vector space V. Okay, and T is the linear operator just mapping a polynomial to its coefficient. Okay, then then we have to give the inner product, um, then we know what is T here. Okay, so now given inner product here, so now for any two polynomial, let alpha is equals to a naught plus a1x plus a2x square, and beta is equals to b naught plus b1x plus, okay, for any, okay, I have to just need to write something. Let px is equals to px is equals to a naught plus a1x plus a2x square, then note that p of 0 is equals to a naught. Now p dash x, which is equals to, it will be a1 plus 2a2x. Therefore, p dash 0 is equals to a1, and p double dash x, what it will be? It will be 2 of a2. Therefore, p double dash 0, 1 by 2, that is equals to a2. So, therefore, one can write a polynomial of degree 2 by this way: p naught plus p dash 0 x plus 1 by 2 p double dash 0 x square. Then the linear polynomial t on p, that is giving as p0 comma p dash 0 comma 1 by p double dash 0. This is the element in the R3. This is the linear operator p. This is the image under the linear operator t of p. So then the inner product, then p mod p inner product q given by this way. This is, I can write it as v. This is can be written as p0 comma p dash 0 comma 1 by 2 p double dash 0. This term with q0 q dash 0 1 by q double dash 0. This is the inner product of the standard inner product of R3. That is equals to p0 q0. This is real polynomial, so we can directly write this way: plus p dash 0 q dash 0 plus 1 by 4 p double dash 0 and q double dash 0 is the inner product induced from inner product of v equals to R3 by the help of uh, t. Okay, so here is, let's look at the questions. So clearly this is the first option is the, yeah, this is the correct options, because this is obviously not correct. So cannot be induced, that is false, because you already look at the, this is possible to induce. Okay, just check the answer. No, this is correct. Okay. So this is the answer. So let's go to another problem. I think I need to introduce something here. Basis. Okay. So before going to an orthonormal basis, we have seen what is orthogonal. So let's do some orthonormal basis. Let V be a vector space. Sorry, V be an inner product space. V be an inner product space over a field F. Then the question is, V be an inner product space over a field F. Then a set alpha I is coming from some indexing set I, is called an orthonormal basis. Orthonormal basis of V. I mean, this can be either countable or this can be either finite or infinite. That is what. If alpha I belongs to R is forms a basis of V, and for any I and j belongs to index set I, inner product of alpha I alpha j is equals to 1 if I equals to j and 0 if I not equals to j. That means uh, that means that means they are orthogonal to each other first. So that gives they are orthogonal to each other. Therefore, they are orthogonal to each other. Therefore, they are orthogonal to each other. I mean, if I take any pair of vectors, then they are orthogonal. Second thing is that norm of uh, alpha I is equals to 1. That means each of them are of uh, order. Okay, each of them are of unit norm. Okay, so that is called orthonormal basis. So let's go to the fifth problem. So what it says, consider a vector W belongs to C such that W star W is equals to 1, where star denotes the conjugate transpose, and let A equals to this something identity minus 2 W W star. Then which of the following is or are correct? Okay. So here question is the W is a column vector. Okay. So therefore W star W is an 1 by 1 vector, but W W star this is an n by n matrix. Okay. So let W equals to W1 all the way W1. Sorry, this is column vector, so we have to write it column as a column, or we can write it as a transpose. W1 all the way Wn. This is belongs to Cn cross 1. This is all are complex numbers, such that W star then W star that will be W1 bar all the way Wn bar. Okay, so that is in Cn. So therefore that implies W star W equals to 1, that implies summation of, then it is given that W star W is 1, so therefore this should imply mod of Wi square, this is equals to 1, I equals to 1 to n. Second thing is that A equals to, it is taken A equals to identity minus 2 W star. Note that W star is an n by n matrix. Note that W star that is equals to Wi Wj bar. This is the ijth entry of a matrix. Be an n by n matrix with ij entries as with ijth entry as Wi Wj bar. This is the ijth entry. Okay, of the matrix W star. So therefore, the what it is asked that the let given that A equals to identity minus 2 W star. So therefore, if I write it as Aij, then what will get? I will get Aij equals to delta Ij minus 2 times Wi Wj bar. Okay, this is the matrix A for which Aij equals to this. Okay, therefore, what is the question? The matrix A is Hermitian or not? Okay, a matrix, Hermitian matrix, n by n matrix, complex matrix A with the entry Aij is called Hermitian, or sometimes self adjoint if A star is equals to A, where A star is complex conjugate and A star is transpose of complex conjugate, a conjugate of transpose, where A star is complex conjugate of transpose. That is, A star its ijth entry, that is ji'th entry with of aij with bar. Okay, so therefore the first question is that whether the matrix A is Hermitian or not. Okay, this is the question. So that means to show A is equals to identity minus 2 times W star is Hermitian, we need to show Aij is equals to Aji bar. Note that Aji bar is equals to delta Ji minus Ji. So 2 Wj Wi bar whole bar. So therefore this is equals to delta Ji minus 2 into Wi Wj bar, that is again Aij. So therefore A is Hermitian. First option is correct. Okay. Second is that the columns of a function orthonormal set of the vectors Cn or not. So as we have seen that, so column vectors. So second is that note that column vectors of C is column vectors of A are Ci, that is equals to A1 AI1 all the way AIN. This is the column vector. So now if I take two column vectors, so to let's take two column vectors Ci and Cj. So if they are so to show C1, C2 all the way Cn are orthonormal, we need to show so that Cij, this is standard inner product of R2, Cn, that is equals to 1 if I equals to j and 0 if I equals not equals to j. So now Ci inner product with Cj, that is equals to, one can write it as a column vector. That is equals to the column vector, that will be summation of Aij and CICK. I'm writing as CICK. Okay, CICJ. I'll write CK. CJ. AIK. AIK. CJK bar. Right? This is K equals to 1 to N. Okay. This is not CJK. CJK is the jth column. So jth column is AJK. I think I have written correctly. Yeah, I have written correctly. So therefore, note that this IK minus 2 Wi Wk bar, this is the first entry, and this is delta Jk minus 2 Wj bar and Wk, right? This is summation K equals to 1 to N. So therefore, what we will get, K equals to 1 to N delta Ik delta Jk minus 2 times, if I run K equals to 1 to N, so let's break K equals to 1 to N. K equals to 1 to N, it will stop at I, and we will get just a minute. Oh, we will stop at I, that is equals to Wj bar Wi. Okay, next is that minus 2 times, if I run K equals to 1 to N, this product of this, and if I run K equals to 1 to N, so when K will be J, only that situation this will be 1, and so therefore in that situation it will survive. So this will be Wi and Wj bar. Okay, the last one is that minus 4 wi wj bar with summation of wk square k equals to 1 to n. But note that w is a vector for which summation of w star w, that is summation of mod wi square, equals to 1. So therefore this will be 1. So this is equals to whatever we have, k equals to 1 to n. So k equals to 1 to n. If we run, so if I and j are 1, then it will be, I mean, if k equals to I, then it will, this one, I mean, if I and j are 1, so there it will be 1. I and j are equal, then it will be 1. Otherwise, it will be 0. Okay. So, so this is equals to, one can write as the 0. Let's take I not equals to 0. So 0 minus 2, this is 4, this is 4 wj bar wi minus 4, or this will be plus 4 wi wj bar, that is equals to 0 if I not equals to j. If I equals to j, it will be 1 minus 4 wr wj wr plus 4 wi wj bar, this is equals to 1 if I equals to j. Therefore, columns of A are orthonormal vectors. Therefore, columns of A forms an orthonormal basis of Cn, because A is an n cross n matrix and columns are linearly independent, and they forms A, because if vectors are orthogonal, if a set of vectors are orthogonal, they are linearly independent. Okay, so therefore it will be column vectors of A forms an orthonormal set of vectors in Cn. Okay. Now, second is that the matrix is diagonalizable over C. Third is that there exists some x belongs to Cn which is not in the linear span of the columns of A. As columns of A forms an linear basis of A, so therefore this option is not correct, because therefore as these columns of A forms a basis of Cn, therefore option B is not correct, because any vector of Cn can be written as the linear combination of columns of A. Okay, so that's why it is false. Now, third is that the matrix A is diagonalizable over C. Okay, this is diagonalizable over C. Why this is diagonalizable over C? Because why A is diagonalizable over C? Okay, this is diagonalizable over C because um, the matrix A is diagonalizable over C. Why the matrix A is diagonalizable over C? This is diagonalizable over C. Okay. Um, what are the matrix? why it will be diagonalizable. Okay. I think W1, W2, Wj, Wn, these are eigenvalue, but this can be equal as well. Okay. Matrix is diagonalizable. It will be diagonalizable as well, but why it will be diagonalizable? The matrix A is diagonalizable over complex field C. Okay, okay. This W star, W W star, this is itself is a matrix that I understand, but this matrix itself is diagonalizable, I think. If that is diagonalizable, so enough to show that W W star, to show that A is diagonalizable, it is enough to show that W W star is diagonalizable, right? So to show W W star is diagonalizable, we need to show that one, for example, if I take 1 comma 0, W W star, W, W, 0, this is the matrix. This is obviously diagonalizable. Okay, getting what is diagonalizable now. Mm, it is clear that trace is 1, that's true. Okay, I think better to just a minute. Now the matrix is diagonalizable. Just a minute, let me think. Actually, this is something known fact. It's symmetric matrix are diagonalizable. Even more generally, normal matrix that is which is not done yet. That those matrices are diagonalizable. That we have to. A being symmetric matrix, A is diagonalizable. Being a symmetric matrix, or sorry, Hermitian matrix, it is diagonalizable. Otherwise, we have to do some more thing. Hermitian matrix, it is diagonalizable. Moreover, any Hermitian matrix is diagonalizable. Normal matrix is diagonalizable. Okay, let's go to some next problem. So this is already done. This is very interesting. With the basis of V and beta with the corresponding, I'll do this one. Okay, but before that, we just I need to go some facts. Let alpha 1, alpha 2 all the way, or Gram-Schmidt orthogonalization. What it says, Gram-Schmidt orthogonalization. But let some facts. Let alpha 1, alpha 2, alpha n. Okay, let's take V be an inner product space over a field F, and let alpha 1, alpha 2, alpha n are orthogonal vectors in V, then they are linearly independent. They are linearly independent. Why this is? We will prove this one. Why this is? Let's take beta equals to Ci alpha I summation of I equals to 1 to n for some Ci belongs to the field F. Okay, that implies beta with alpha I inner product that is equals to summation of alpha j I equals to 1 to n Ci alpha I alpha j Cj alpha j. This is the okay. So therefore, as alpha I, as this is an orthogonal vectors, so that implies that inner product of alpha I alpha j that is equals to 0 if I not equals to j. This is the thing. So therefore, one can write this will be that Cj. Okay. Sorry. I have written wrongly. This is I equals to 1 to, and this is equals to C. This is equals to Ci alpha j. So this will be Cj inner product alpha j. Okay. So therefore, this will give that as alpha I alpha j are not equals to 0, this gives that inner product alpha j that is equals to norm of alpha j square that is not equals to 0. Therefore, this gives that Cj is equals to inner product of beta alpha j by norm of alpha j square. Okay, so this gives that if summation of Ci alpha I equals to 0, I equals to 1 to n that is equals to beta, this implies that beta with inner product alpha j that equals to 0, that implies that Cj equals to 0. This gives that this particular set of vectors alpha 1, alpha 2, alpha n is linearly independent. Okay, but interestingly here one can look at if beta is equals to summation of Ci alpha I equals to 1 to n. Note that if alpha 1, alpha n are orthogonal vectors, orthogonal set of pairwise orthogonal vectors, set of pairwise orthogonal vectors in V, then alpha I, alpha j, sorry, set of pairwise vector orthogonal in then for any, then if beta is equals to this, beta is the linear combination of this particular vector, this set of vectors alpha equals to 1, then for some ci belongs to f, then beta is equals to, it can be written as I equals to 1 to n inner product of beta with alpha I by norm of alpha I square dot alpha I. So therefore, this is an interesting set of explanation we are getting. I mean, we are getting a vector beta. Suppose I want to find a vector beta as a linear combination of a set of orthogonal vectors alpha and alpha to alpha n, then we can get a interesting type of this equality. Okay, so now if we have just a linearly independent set of vectors, we will may not get this type of interesting facts. Suppose so, but if we have only, note that if we have only a set of linearly independent vectors, linearly independent vectors, then we may not be able to write that arbitrary vector beta in this. We may not be able to write beta in this form. To write beta in this form. So the question is that suppose we are giving a linearly independent set of vectors. So how one can get a new set of vectors which is which will, I mean, suppose we are giving a set of linearly independent vectors, and those vectors generates a vector space, obviously subspace, and suppose we want a new set of vectors which is orthogonal, and they also generate the same set of same vector space. Okay, so let and then the way which I mean the way which is used to get those type of vector space, those type of vectors, orthogonal vectors, are called the Gram-Schmidt orthogonalization process. Let alpha 1, alpha 2, all the way alpha n be a set of linearly independent vectors. Linearly independent vectors in an inner product space V. Then consider alpha beta 1 is equals to alpha. Beta 1 is as it is, okay, and beta 2 is equals to alpha 2 minus alpha 1 with inner product, or alpha 2 with inner product alpha 1 by norm of alpha 1 square into alpha 1. And in this way, beta 3 is equals to alpha 3 minus alpha 3 comma alpha 2. Okay, we are getting this way. Okay, now let's write beta 3. Beta 3 is equals to alpha 3. We can write it, this is something new form, that is alpha 2 beta 1 by norm of beta 1 square into beta 1. That is alpha 3 minus alpha 3 comma beta 2. We know what beta 2 is now. Norm of beta 2 square into beta 2 minus alpha 3. We know what beta 1 is. Beta 1 square into alpha 1. In this way, we can get beta n is equals to alpha n minus, or I can write it as an arbitrary vector, beta I plus 1 is equals to beta I alpha I plus 1 alpha I plus 1 minus summation of j equals to 1 to I inner product alpha I plus 1 with alpha I by or k equals to 1 to I k norm of alpha k square into alpha k, and this process, and then note that if in this way we will get some vectors. Okay, note that this beta 1 beta n generates same vector space which is generated by alpha 1 all the way alpha n, and 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 this beta 1 beta 2 are this beta 1 beta 2 are orthogonal. So let's check why this is orthogonal. If I take beta I with inner product beta j, then what is there? It will be, first will be the beta alpha I minus inner product of alpha I beta I norm of okay. This is chosen in such a way. Why this is two? Okay, let's go step by step. Suppose we have beta 1. Okay, now I have to show that beta 2 with beta 1. What is this? This is equals to alpha 2 inner product of alpha 2 minus alpha 2 with beta 1, that is same with alpha 1, okay, by norm of alpha 1 square into alpha 1 with beta 1, that is alpha 1. So if you do the usual usual properties of inner product, we will get this one. Note that this norm of alpha 1 square inner product of alpha 1 is same. So therefore alpha 2 inner product alpha 2 alpha 1 minus alpha 2 alpha 1, that is equals to 0. Now we get beta 3. So beta 3, I have to check beta 3 beta 2, that is equals to 0, and beta 2 beta 1, that is equals to 0. So let's first check beta 3 beta 1. Beta 3 says that is equals to alpha 3 minus alpha 3 with beta 2 by norm of beta 2 square into beta 2 minus alpha 3 with beta 1 by norm of beta 1 square into beta 1 inner product with beta 1, right? So note that first term will be alpha 3 with beta 1, that is beta 1 is alpha 1. Okay, next term is that alpha 3 beta 2, but we know that by norm of beta 2 square, but now beta 2 with beta 1 inner product. And the last term is alpha 3 with beta 1 by norm of beta 1 square into norm of beta 1 square. Note that this term is equals to 0, that we have already seen here. So therefore note that, and this term is equals to this term. So therefore alpha 3 inner product beta 1 is equals to minus alpha 3 inner product beta 1, that is equal to 0. Similarly, one can show that beta 3 with beta 2, what it will be, beta 3 is alpha 3 minus alpha 3 with beta 2 inner product norm of beta 2 square into beta 2 with um, okay, next term is the minus alpha 3 with beta 1 norm of beta 1 square into beta 1 inner product with beta 2, right? Note that using linearity, we get alpha 3 with beta 2 minus alpha 3 with beta 2 by norm of beta 2 square into inner product of beta 2, that is norm of beta 2 square, minus alpha 3 with beta 1 by norm of beta 1 square, beta 1 beta 2. But note that beta 1 beta 2 is already 0, we have inner product is 0, so and these two terms are equal, so therefore we will again get alpha 3 inner product beta 2 minus alpha 3 inner product beta 2. So therefore in this way one can check, therefore one can check beta I plus 1 inner product with beta k inner product, that is equals to 0 for all k equals to 1 to all the way I. Therefore these vectors beta 1 beta 2 are orthogonal set of vectors. And this process is known as the Gram-Schmidt orthogonalization. This process of orthogonalization is known as Gram-Schmidt orthogonalization. So let's do some problem, okay? This is not the problem. This is the problem. So what is the question here? It says that let V be a vector space. Let V be a vector space that is R3 with Euclidean inner product equal to the standard inner product, and B and it is says that um, let the basis, this is giving beta 1 beta 2 beta 3 as the elements, and corresponding orthogonal basis obtained from B by Gram-Schmidt orthogonalization. So here it is giving the basis beta be a basis of V, and beta 1 beta 2 be the corresponding orthogonal basis obtained from the Gram-Schmidt orthogonalization. So let's take alpha 1 is equals to 2 1 2, alpha 2 is equals to 4 6 2, and alpha 3 is equals to 10 2 minus 6. So okay, and let and no recall that inner product of x and y is equals to this, here all things are in real, so therefore it will be x1 y1 plus x2 y2 plus x3 y3, where x is equals to x1 or x1 x2 x3, and y is equals to y1 y2 y3, that is in R3. Okay, so now the question is that I have to do the Gram-Schmidt orthogonalization. Okay, one remark I just want to make here is that we have seen a Gram-Schmidt orthogonalization process there. Suppose we are given a set of vectors, not necessarily linearly independent. Okay, here the set of vectors alpha 1 alpha 2 alpha n, what is given, this is not necessarily linearly independent. Therefore, if we do this Gram-Schmidt orthogonalization process, so I mean, suppose we are giving alpha 1 alpha 2 alpha n, this n number of linearly independent set of vectors, and let's assume that they are not linearly, sorry, we are giving set of n vectors alpha 1 alpha 2 alpha n, and assume that they are not necessarily linearly independent. So therefore these n vectors are not linearly independent, so that means there must exist at least one vector which is the linear combination of all other vectors, right? So therefore if we do the Gram-Schmidt orthogonalization, so we'll reach a stage where the beta I will be 0. So in that situation, I mean, if we do the Gram-Schmidt orthogonalization, first we have done beta 1, second we have done beta 2, and all the we'll when we'll try to find alpha this way, beta is equals to ai minus inner product of inner product of summation of ai uh, summation of ai with beta k by norm of beta k square with beta k is equals to 1 to I minus 1. So here, if, for example, if ai is linearly dependent on a1, a2, ai minus 1, then this beta I will be 0. And ai can be written as a linear combination of a1, a2, ai minus 1. So, using the Gram-Schmidt orthogonalization question, we can also check whether a set of vectors is linearly independent or not. So, we can start with a set of any vectors and do the process. We'll, at the end of the process, we will have a set of linearly independent vectors, well, yes, a set of orthogonal vectors which generates the same space which is generated by a1, a2, an, even if we don't take linearly independent. Okay. So linearly independence is not that much important. But if we want to get a set of vectors which also which is orthogonal and also contains n number of vectors, then we need linearly independent. Okay. So we do the Gram-Schmidt orthogonalization process here. Okay. So let's first take beta 1 is equals to 2, 1, 2. Okay. So beta 2 will be alpha 2 minus alpha 2 with beta 1 by norm of beta 1 square into beta 1. So we need three factors. We need two factors, alpha 2 beta 1, that I want to know. So what is alpha 2 here? Alpha 2 is 4, 6, 2 and beta 1 is this. So 4, 8 plus 6 plus 4, that is equals to 18. And a norm of beta 1 square, that is equals to 4 plus 1 plus 4, that is equals to 9. So norm of beta 1 is equals to 3. So therefore this will be alpha 2 minus 18 by 3 into beta 1, which is again an alpha 1. So therefore this is 3, 6. So alpha 2 is given as 4, 6, 2. 4, 6, 2 minus 6 into 2, 1, 2. This is the vector. Okay. Oh, I think I have made some mistake. Okay, what it is asking here is the Gram-Schmidt percentage, then beta 2. What is the beta 2? B is equals to 2, 1, 2, 466 and 10, 2 minus 6. So beta 1 be the corresponding orthogonal basis obtained from B by Gram-Schmidt orthogonal basis. So beta 1 is equals to 2, 1, 2. Beta 2 is equals to alpha 2 minus alpha 2 into beta 1. Beta 1 is 2, 1, 2, alpha 2 is 4, 6, 2. So 4, 2, 8, 6 plus 4, 18. And norm of beta 1 square, that is 4 plus 1 plus 4, that is 8 plus 1, 9. See. And so 18 by 3. Oh, beta 1 square it is. So sorry. Beta 1 square it is. So it is 18 by 9 into, this will be 2, 1, 2. That is, this is 2. So that means 4, 6, 2 minus 4, 2, 4. So what will get that is 0, 4 minus 2. 0, 4 minus 2 is the answer. This is the answer. So automatically all other will be incorrect because this is something unique. If we don't change the order, okay. So this will be unique then, okay. Okay. So we will not do Gram-Schmidt orthogonalization process again, but we'll take another sum problem. So this is irrelevant. We'll come back to problem 7 if we get the enough time. So let's go to problem number 9. Another problem. Yeah. So, but before going to this problem, we will just say Cauchy-Schwarz inequality. So now let Cauchy-Schwarz inequality. This is very important. This is very useful and famous because there is lots of similar manner. Okay. What it says, let V be an inner product space with some inner product, standard notation we will use, inner product space over a field alpha, over a field F. Then what will satisfy first is that C alpha, then C alpha, then what I'll just write, I'll write only one. Um, Alpha beta inner product that is less than equals to norm of alpha square, not norm of alpha, so norm of beta. We know what is norm, okay? And here this is called Cauchy-Schwarz inequality. Okay, for all alpha and beta, it's coming from the vector space V. Okay, how to write beta? So how let's beta is equals to beta gamma is equals to let's take gamma is equals to beta minus inner product of beta alpha by norm of alpha square, or you can write it as a beta alpha, norm of alpha square. Okay, okay. So with alpha, we are writing this way. Let's write this a vector. This is a vector. This is obviously in the vector space V because this is linear combination of beta and alpha. So note, therefore, we know that as we know that for any element in vector space V and gamma not equals to 0, we can write any element vector space V, norm of gamma square is greater than or equals to 0. If gamma equals to 0, then it will be 0. If it is not 0, then it will be strictly positive. Okay, so then inner product of beta minus beta alpha inner product by norm of alpha square into alpha with beta minus beta alpha with norm of alpha square into alpha is greater than or equals to 0. That is equals to norm of gamma square, that is equals to 0. Note that we will use the linearity in first variable and second variable, conjugate linearity in the first variable and second variable on the right hand side. So what we'll get? We'll get norm of beta square, that is inner product of beta beta. Second is that this one with this one. So therefore, inner product of beta alpha, that is bar, by norm of alpha square into beta alpha minus inner product of beta alpha by norm of alpha square into alpha beta plus mod of or beta alpha square. Okay, this will be mod because one is the conjugate and another is, this will be 4 into norm of alpha square. This is greater than or equals to 0. So what we will get, norm of beta square minus mod of beta alpha square by norm of alpha square minus, note that this is also norm of beta alpha mod square by norm of alpha square plus mod of beta alpha square by norm of alpha square. This is greater than or equals to 0, as inner product of alpha beta is equals to inner product of beta alpha bar. Okay, so what we'll get, one will cancel out. So what we'll get, that norm of beta square greater than is equals to mod of inner product beta alpha square by norm of alpha square. So therefore what we'll get, mod of beta alpha square is less than equals to norm of alpha square into norm of beta square, and that implies inner product of beta alpha mod is less than equals to norm of alpha into norm of beta. So this is the Cauchy-Schwarz inequality. So with this inequality, we'll prove one problem. So we know that let V be the vector space of all real valued functions on 0, 1, real valued continuous functions. Let V be the vector space of all real valued continuous function on 0, 1, close interval 0, 1. Okay, then If inner product fg given by 0, 1, f of x, g of x dx is an inner product on V, you can check, but note that this continuity will be useful. Otherwise, you will not able to prove this is the inner product. Then homogeneity will not be, sorry, non-negative definite will not be proved without continuity. So then the question is that what we have seen that by Cauchy-Schwarz inequality, Cauchy-Schwarz inequality, we get by Cauchy-Schwarz inequality we get mod of f g is less than equals to norm of f norm of g. That is what it is says is that inner mod of 0 to 1 f of x g of x dx, that is less than equals to 0 to 1 mod of fx square whole to the power half mod of 0 to 1 mod of gx square whole to the power half. This is dx, this is dx. Okay, so now you will use this one. So let's see which one is satisfying. So um, but which one will satisfy? I think it should be half. There must be some problem, I think. Okay, so let's check each of them. Okay, starting with the options A. What is option A says? 0 to 1 x fx dx, right? This is the thing. I think there is a mistake. This will be 2. This is 2. So this can be written as 0 to 1 x, this is the first function, and f of x, this is the second function. So one can be written as 0 to 1 mod of x square dx whole to the power half and 0 to 1 mod of fx square dx whole to the power half. So note that this is equals to 0 to 1 x square, this is real value, so there is nothing about mod. So this will be x to the power x cube by 3, 0 to 1, this whole to the power half, and 0 to 1 mod of fx square dx whole to the power half. So this will get 1 by root 3 into 0 to 1 mod of fx square dx whole to the power half. So this is correct actually. 0 to 1 mod of fx square by 3 into dx whole to the power half. Okay, so therefore this is correct. This is the correct one. Okay, so this is correct clearly. Second one is that this is not possible at all. This is not possible. So this is false. Third one is that why both of them is simultaneously correct. 1 by 3 or 1 by 4, which one is the bigger? 1 by 3, 4 is greater than 3, so 1 by 4 is less than 1 by 3. So this is not necessarily true. So but okay, I don't know what is the, okay, let me check once the all other options. It is saying that 0 to 1 fx. This is correct options. Why the second option is correct? If one takes, it will be 4. 4. Correct option is 1. Which of the following statement is or are correct? Only one option is possible to be correct. I think this is correct. There must be some problem. So all other options will automatically false. Okay, because there can't be other options can't be true, because I think one can give an example. For example, for this one can take f of x is equals to x, and what will get? This will get x square. Okay, so in that situation, one will get that. Let's check whether these are satisfied or not. X square 0 to, okay, this will be left hand side will be, let's just quick check. Left hand side will be x square next to the 3 by 3. Okay, that is equals to 1 by 3, and right hand side will be mod of fx square, that is x square. Oh, so 1 by root 3. 1 by root 3 is bigger than 1 by 3. That's true. So if I take x square, fx equals to x square, then it will be x cube, that will be 1 by 4, and this side will be x square I have taken, so x to the power 4 means 5 by 5 whole to the power half, so 1 by square root 5. So which one is bigger? 4 is bigger than root 5, so 1 by 4 is less than 1 by root 5. I think one option is the correct option. All other is not possible to be true. One can create an example for each of them. Okay. Okay. I just want to give one example for some, at least for one of them. Um, what example one can give? Where the left hand side is not. Okay. Let's take fx is constant function. Yeah. Yes. For first one, for option B, take fx is equals to 1. Then 0 to 1 fx dx, this is equals to 0 to 1 x dx, this is equals to x square by 2, 0 to 1, that is equals to 1 by 2, and gx is equals to, and the right hand side 0 to 1 fx whole to the power half, that is equals to 1. So 1 is bigger than, that's true. It's true, just a minute. X fx. Okay. Yeah. B option is correct. That's why it is. Note that I got it. Why B option is correct? Because option B is only correct. All other option is not correct. B option is correct. Why B option is correct? Because note that 1 by square root of 3. Note that square root of 3 is greater than 1. So that therefore 1 by square root of 3 is less than 1. That means 1 by square root of 3, 0 to 1, f of x square whole to the power dx whole to the power half, that must be less than equals to 0 to 1 f of x square dx whole to the power half. But so therefore this will give me that 0 to 1 x fx dx, this is less than equals to mod of this less than equals to 0 to 1 f of x square dx whole to the power half. So B is correct. For C and D, one can give some examples. For C, one can for C for C note that take f of x is equals to 1. So then the first option is 0 to 1, f of x dx that must be equals to x square by 2, 0 to 1 that is equals to 1 by 2. And the second option is that but 0 to 1 mod of fx square by 4 whole to the dx whole to the power half that must be equals to, if we take fx equals to 1, this will be 4, 1 by 4. So that implies 1 by 2 is not less than 1 by 4. But 1 by 2 is not less than 1 by 4. That implies that 0 to 1 x fx dx mod is not less than equals to 0 to 1 mod of fx square by 4 dx whole to the power half. Similarly, same example will work. So therefore option C is false. Therefore option C is false. Same example will work for option D, and option D is false. Same example, if we just take, then we can check that 1 by 2 is not less than 1 by 8, so therefore that will also be false. Okay, so this is all. So already we are, so we'll stop here. Okay, just more one one more problem. I'll just, no, we'll stop here.